ARM7 we have got a much more complex architecture compared to say 8051 or 8085, in the sense that it has got the data bus which is 32 bit and the address bus is also 32 bit, and this there is no multiplexing of address and data bus. So, they are separate. So, address bus is 32 bit here and data bus is 32 bit here. Now, we have got internally there is a internal bus. So, one bus is the ALU bus which we call A bus, and also it is A bus coming from the register bank, and this ALU bus is coming out of the ALU and it is feeding the register bank as well as the address registers. So, sometimes we will like to take this register bank values from some of the values from some of the registers to do the operation. So, in that case this A bus will be utilized, and for storing the result back. So, result may be stored back onto the register in this bank register, or it may be onto some address register for some further addressing. And we have got a separate incrementer. So, this is another important thing that you see here, there is an address incrementer. So, unlike 8051 where we have got the same ALU which is doing the address incrementation after each instruction, here that PC increment operation is done by this incrementer module. So, it is totally separated from the other computational overhead of the processor. So, this ALU is responsible for doing the normal operations of the instructions, and this incrementer is for address incrementing. So, then its output can feed to some register bank or it might go to some address register. So, address register is actually the register which will hold the address which is visible to the outside world. So, whatever be the instruction, if ultimately this memory has to be accessed, the address register will contain the address of the location. So, if you are trying to write some data, then this write data register will have the value in it that you want to write. So, after putting the address here and data here, so you can say enable out. So, this enable out will be so this will enable this output onto the data bus. Similarly, if you are trying to read something from the memory, then this is coming to this instruction pipeline as well as read data register. So, we will explore this instruction pipeline part later, but essentially the instruction when it is coming. So, in case of 8085 or 8051, we have got a single instruction register where the instruction opcode is coming, but here it is a more pipeline stage. So, there will be number of pipeline stages for the operation. And this read data register. So, this is if you are reading from data from the program memory. So, it will be coming into this, and internally you see that we have got a booths multiplier for doing the multiplication operation. So, for multiplication instruction, so we have got booths multiplier. So, that way the ALU is relieved from doing that operation, and we will see that multiplication operation has also been optimized, so that it takes much less number of cycles compared to normal multiplication. Then the barrel shifter is there. So, I have already said that you can shift the operand in a single instruction before doing the arithmetic logic operation. So, you can do a shifting of the operand. So, multiplication by 2 or division by 2. So, multiplication and division by powers of 2. So, that can be done by this barrel shifter, and many a times particularly in signal processing algorithms. So, we will find that there are many operations that we do are multiplication and divisions by powers of 2. So, those operations can be done very easily in this type of architecture. So, coming to the pipeline part. So, this ARM has got it is a pipelined architecture. So, pipelined architecture, what do we mean by that is that suppose we have got some functional block. Okay. Suppose we have got some functional block like this, and this functional block it will have some delay. So, it has got a delay of say d unit. So, it has got a delay of d unit. Now, in a pipelined operation, what is done is that this delay, this module is divided into a number of sub modules. Fine. So, I have got this first module. So, this is the say I have got this first module which is say of delay d1, then the output of this stage goes to the next stage, that has got a delay of d2, and the third output of that stage goes to the third stage, that has got a delay of d3. So, the original block of delay d, it is divided into 3 modules like this. So, previously we had a single module with a delay of d and the inputs were coming to that. So, if the delay is d, so you can operate this module at a frequency f equal to 1 by d. So, after every d time unit, so what the input data when it is coming here, so after d time unit the value will be available here. On the other hand, if I do an implementation like this, then what happens is that this individual module delay, so d1, d2 and d3. So, the first data item that you have here, so that will see a total delay of d1 plus d2 plus d3 as the, so that is equal to d. So, that it will see that amount of delay. But when this first data item has been has reached the second module, so the second data item can be fed here, and after some time the first data item will reach the third stage of processing. So, then this will be doing the second one and this will be doing the third data item. So, that way if you have a continuous flow of data, then you can see that after every small amount of time, so this data will be outputted. Like say if this d1, so if suppose I have got this d, which is the maximum of all these 3 values d1, d2 and d3, then we can say that after every d time unit the next sample next output will be available here, because when the first data is coming out, the second data is already here. So, second data will be coming out after the delay of d3. Similarly, the third data will be coming out after another delay of d3, like that. So, if d happens to be the maximum of these 3 stage delays, then after every d time unit the data will be available at the output. So, this is the concept of pipelining. So, this pipelining is used in different processors. We have already seen that fetch, decode, execute pipeline in instruction execution. In case of ARM processor, so that it has been made much, it has been used much more, and naturally since this original functionality d has been divided into 3 steps, d1, d2 and d3. So, d the small d value is often much less than the capital D value. So, that way I can do the processing at a much higher rate. Okay. So, coming back to the discussion, this has, so ARM has got this pipelining feature, and there are various number of stages of pipelines that are available in different versions of the processor. Like ARM 7, it has got 3 stage pipeline, ARM S and ARM 9 TDMI. So, they have got 5 stage pipeline. Then ARM 10 has got 6 stage pipeline, ARM 11 has got 8 stage pipeline. So, slowly the number of pipeline stages have been increased, and with the increasing number of pipeline stages, the advantage is that we can have faster processing. So, first one is the 3 stage pipeline. So, this is the classical fetch, decode, execute pipeline. So, it is same as other processors that we have. So, like 8085, 8051, so all of them they do this fetch, decode, execute pipeline. So, first stage is the fetch stage. So, this fetch stage is responsible for reading the content from the memory. So, it reads the instruction from the memory and it will increment the program counter or instruction address register. So, in case of ARM, so in this program counter will call instruction address register. So, that value is incremented so that it can point to the next instruction. The first stage is the fetch. Second stage is the decode. So, decode will decode the instruction. So, it will understand what is the meaning of the opcode and it will prepare the control signals accordingly. So, if you look into this diagram, so this after this instruction has reached here, so it goes to this instruction decoder and control logic, and it generates a number of control signals for various modules that we have here. Some of them are for some of them are we will explain these remaining terms later, but this is they are coming to the these signals will also control the operation of this control logic, but overall the instruction reaching here is decoded here, and these control signals are generated for the remaining module, for other modules that will do the operation. So, the second stage you will do this decode and prepare the control signals. The third stage it does the actual work. So, what is the actual work? So, it has to read operands from the register file, like so it may be that I want to add the content of 2 registers. So, those 2 register values will be should be available to the ALU, then the ALU will do the operation and then it will write back the value onto the value of this of the modified register. So, this way we can do this operation, okay. The operation can be carried out, and in case of ARM, so you will see that whenever we are doing an arithmetic logic operation, so the operands are always from the register bank. So, you cannot have it from external memory like that directly. So, that is why it is called it has it is this here we are mentioning explicitly that it is doing the operation on the register file. So, 3 stage pipelining, the difficulty that we have is that if every data transfer instruction, it will cause the pipeline stall. So, pipeline stall is something like this, that so I have got this pipelining. So, if the resource is busy, like say fetch, decode and execute. So, these 3 stages are there. Now, if this execute stage is also asking to access memory. So, this is also asking to access memory, like the instruction that we have may be to save the content of some register onto some memory location. So, that way this instruction will be using the memory bus. So, I cannot fetch the next instruction. So, there will be this fetching part will be stalled. So, this type of pipeline stall will occur, and if you look into the operations that we have out of these 3 stages, the execute stage will take the maximum amount of time, because it may be doing some complex operation. So, so this is the problem. So, we have got this every data transfer instruction. So, we will have a pipeline stall, because the next instruction cannot be fetched while the memory is being read or written. So, how to solve this problem? So, this problem is solved by going to the Harvard architecture, in which the program memory and the data memory, they are separate. So, instruction memory and data memory are separated. So, we have got separate address bus and data bus for 2 types of memories. So, if previously the structure was like this, if this was the processor, the ARM processor, and we have got this as the memory, this as the memory. So, we have got this address bus, data bus, control bus, like that. Now, in the Harvard architecture, you know that it is made like this. If this is the processor, ARM processor, now we have got the program memory and the data memory, they are separate. So, this is program memory and we have got the data memory, which is separate. Now, what will happen is that when the ARM is asking for program, so it will access the program memory. So, it has got the address bus, data bus and control bus for the program part, and similarly it will have address, data and control bus for the data part, for the data memory access. So, this way we have got this the 2 memory, they are separated and the buses are also separate. So, you have got the flexibility now that we can go for this this data access will not hamper the fetching of the next instruction from memory. So, instruction and data memory are separated. Third thing that is done is that the next stage is to somehow make this operation of this the execute phase simpler. How do we do this? This register read step is moved to the decode stage. So, in the previous case, the execute operation, the first thing that it had to do is to get the operands from the register file to the ALU for the operation. So, this is simplified, and now we this register read is going to the decode stage. So, decode stage was previously less lightly loaded. now the load has been increased to make the balancing between the stages. So, execute stage is also split into 3 sub stages, one for performing arithmetic computation, then memory access, and then write result back to register file. So, these are the 3 stages into which this the execute stage is also divided. So, you have got this fetch is there, decode and register read, that constitutes one stage, and this execute stage is divided into 3 stages. So, as a result we have got 5 stage pipeline. Okay. Here is 3 and decode 1 and fetch 1. So, 5 stage pipeline. So, this as it is there is a balancing in the pipeline that we see now, because the decode stage was very lightly loaded. So, that has been given enough job to do now. So, it reduces the CPI. So, CPI stands for clocks per instruction. So, how many clocks are needed per instruction? So, in a pipeline fashion, so number of the instructions are executed in a pipelined way. So, you can execute more number of instructions. So, ideally we would like to have 1 clock per instruction, because if I have got one instruction taking say 10 stages and the architecture is a 10 stage pipelined architecture, then after every clock cycle one instruction should be complete. So, that way the ideally the CPI value should be 1, but it is not possible, definitely it is not possible, because of the different stage requirements of these instructions, and the number of pipeline stages will not always match exactly with the size of the execution time of the instruction. So, that as a result it cannot be 1, but it will reduce the average number of average CPI value. However, it leads to another problem which is known as data forwarding. So, what is data forwarding? So, it is like this. So, what we have done is we had 3 stage pipeline, this fetch, decode and execute, fetch, decode and execute, and this execute was 3 stages. The first stage was register read, then the next stage was the computation, and the third stage was the writing back. So, these were the 3 stages. Now, what we have done in the modified version, we have got this fetch, this is there, but this decode is made complex. So, decode has got 2 stages now, decode and this register read. Decode and register read, they are the 2 stages, and then we have got this execute one, that has got this computation and this writing back, these 2 are there. Now, you can understand the problem, because what can happen, suppose I have got an instruction like R1, say R1 equal to R2 plus R3, and we have got an instruction like say R1 equal to R2 plus R3, and the second instruction is say R4 equal to R1 into R5. So, what is happening is that you see this R1 value that is computing. So, it is available if this is instruction 1 and this is the instruction 2. So, when the instruction 1 comes to this stage, or here when the instruction 1 comes to this phase, then only the R1 value will be updated. But when instruction 1 is in this stage, instruction 2 is in the previous stage of the pipeline. So, what is happening is that the instruction 2 is actually not here, instruction 2 will be in the computation phase. So, by this time instruction 2 has already got the value of R1. So, instruction 2 requires R1 as one of the operand. So, by this time instruction 2 has already accessed R1, and but that value is not correct, because in this program what we mean is that whatever be the output of summation of R2 and R3, so that should be the content of R1. So, here I am getting some older content of R1. So, we have to have some sort of scheme which is known as data forwarding. So, what happens is that when the compiler will see that there is a situation like this, that some operand value that is being used which is not yet stabilized. So, it is the destination does not have its value yet. So, between the stages there should be some way by which this data is forwarded. So, this ALU output R1 should somehow be fed as the operand for the next instruction. So, the architecture supports this facility, and it is the compiler's job to identify those situations and accordingly mark that the data forwarding should take place at those places, and then the architecture will be, the control words will be generated, so that it is taken care of. So, that is the 5 stage, that is about the 5 stage pipelining. So, data forwarding may be necessary between the pipeline stages to resolve data dependency. So, whenever between stages we have got data dependency, so either we have to stall the pipeline, so that the previous instruction is over, then only I go into the fetching of the next instruction or executing the register read of the next instruction. That, so for that much time we have to wait, that is pipeline stall, or we have to do some sort of data forwarding. Okay, so, both are possible. So, next we will look into sixth stage pipeline. So, ARM 10 has got 6 stage pipeline. Here the decode is split into 2 pipeline stages as earlier, the decode and register, and decode stage performs the decode operation, and the register read will perform the register the reading the register operation. And but now a separate adder is introduced in the execution unit to take care of this multiply accumulate type of instructions. So, instruction decode, previously the instruction decode was done in one stage, consists doing both decode and register read together. Now, it is divided into 2 stages. So, you have got this decode and register read may put together, put separately into 2 stages. So, you get some 6th stage pipeline. And also, so the separate adder has been introduced for multiply accumulate type of instruction. So, multiply accumulate is something like this. So, multiply accumulate will be doing like this. So, suppose I have got an operation like this. So, y equal to sigma a I x I. So, this is a very common operation in case of signal processing, where these x i's are the signal samples, these may be signal samples, and these a i's are the filter coefficients. So, this is very common. So, whenever we are doing any computation in signal processing, so this is the filtering operations, so they often do like this. Now, you see that if you want to write it in a if you want to do it by means of a hardware, then what is required is you should have this register which will hold these A values. So, these are the A values. You should have another bank of locations where it will have the X values, and then the successive values should be fed to this adder. They will be fed to the adder, and A I and X I, that will do that multiplication. Sorry, this is a multiplier. So, this A I X I will be multiplied, and then it should go to an adder where it will be doing the addition part. So, this is the adder. So, this is the Y register, and this value should come here, and we should have a structure like this. So, this previous value will be added, okay, and it will be doing like this. Now, if you do not have this particular structure available in the within the processor, then what you have to do is you have to write a program where it will be for doing this intermediary calculations, and then it will be adding it with y. So, that way it has to be in a program, we have to do that. So, if I have a single ALU for doing this operation, then we have to use that ALU for doing the multiplication and then addition, then again multiplication, then again addition, like that single ALU has to be used. So, in case of ARM processor, what has been done is one such module has been incorporated into the system. So, this is called multiply accumulate unit. So, it will multiply the successive data items coming from A I and X I, and accumulate the values in the Y register. So, in the internally, so we have got this hardware available, so that by a single instruction we can do this multiply accumulate type of operation. So, we will see that in more detail the actual instruction when we go to the instruction set of the processor. So, this multiply accumulate is done by a separate execution unit that takes care of this multiply accumulate operation. Then we have the instruction and data buses are now 64 bit. Okay. So, now the ARM 10, so it has got 64 bit address instruction and data buses. So, instead of being 32 bit data bus, so you have got 64 bit data bus, but internal operation remains as 32 bit only. The advantage we get is the accessing the external memory. So, in one access you can get 2 instructions now. So, because each instruction is 32 bit, so you get 2 instructions, and data bus is also 64 bit. So, in one access, so you can get 2 data items. So, that way number of accesses to the outside data memory and program memory will be less, and that will help in reducing the complexity in terms of this power consumption of the system, because bus activity will lead to bus power consumption, and that will lead to at least the heating effect. So, the heat of the temperature of the system may be high. So, as we said that ARM is designed to have low power. So, this is another avenue by which this power reduction is achieved in ARM 10 processor.